Duncan, you're muted. And then I'm going to start the recording. We're up to 51 people. I'll make Elizabeth co-host. Okay. Well, welcome back. I think we're gonna get started. Who's the moderator of this session?
I believe it was Tianli Yuan. Is he? I don't know if he's here. If not, I can moderate.
Okay.
So let's get started. So thank you all for joining the second day. Today's talks are going to predominantly be focused on sort of natural experiments. And so we'll kick off with Graham Feingold's presentation on a research roadmap for marine cloud brightening.
Thanks, Matt. Let's see how quickly I can do this. And does that appear as you'd like to see it?
Yeah, it looks good.
Okay, thanks. I'll keep this fairly brief. I want to discuss what we're calling a research roadmap for marine cloud brightening. And I think you all know what the concept of marine cloud brightening, the deliberate injection of particles into clouds to brighten them and potentially offset some of the greenhouse gas warming. And want to clearly acknowledge here the list of people involved in this work: Michael Diamond, the lead author of a recent PNAS opinion piece, which documents some of the ideas that I'm going to be presenting, and the other co-authors listed here too. Ship tracks are obviously a clear manifestation of aerosol cloud brightening. This is certainly something this group needs no introduction to. The first documentation of ship tracks comes from Conover in 1966, and there's an interesting sentence or two written towards the end of the paper, which I will read here. It appears that cloud enhancement to increase the albedo about 20% over large areas would be artificially possible under certain limited existing conditions by generating liquid cloud through the introduction of Aitken nuclei. And he goes on to say that this might, even if this was desirable, the combustion of large amounts of fuel and its dispersion would be expensive. But he already recognized when documenting these ship tracks that there might be potential for brightening the planet. Now, we asked ourselves why we might consider, or we should, I think, altogether ask ourselves why we might consider marine cloud brightening. The first thing I want to emphasize here is that the priority is to decarbonize, and I think we are all in agreement on that. But various national and international bodies are beginning to discuss climate intervention as a means of preventing the worst effects of global warming. And one might think of this for peak shaving or protecting local ecosystems like coral reefs. And our thinking is that it's our responsibility as a community to organize our research efforts for a topic as important as this. We need to provide the best information to decision makers so that they can go forth and make the appropriate decisions. And also, we see this as a sort of form of self-governance until international governance is established. Any research program into MCB will have to have international governance associated with it. Importantly, we have knowledge of aerosol cloud interactions, much of which is important to MCB. We have similar problems, challenges, microphysics, particle dispersion, activation, liquid water adjustment, adjustments, changes in circulation, etc. And so we're in a good position to provide input to this problem. I've listed in this table just a few differences and in some senses commonalities between aerosol, the broader problem of ACI and MCB. ACI, one could think of it as an inadvertent anthropogenic perturbation. Of course, inadvertent in inverted commas here, because we know what we're doing, and yet we continue to produce large amounts of particulate matter that are affecting our climate and our clouds. But MCB would be the deliberate seeding of clouds. In ACI, we have this sort of inherent aerosol meteorology covariability. We don't sort of think about when aerosol is emitted. It's emitted as society emits it, and there is that covariability with the meteorology. But with MCB, we're actually attempting to control the aerosol meteorological covariability. And of course, we're also trying to control duration and timing, or thinking of controlling duration and timing. ACI would emit, or does emit, particles of different composition and mixing state, whereas MCB emits sea spray, which then evaporates on its way up to the cloud. And when it gets to the cloud, in its drier state, will activate. ACI, well, we emit a range of aerosol sizes, whereas MCB would try to optimize sizes for maximum brightening. When it comes to the effects of marine cloud brightening and aerosol cloud interactions for that matter, there are local effects that scale up towards regional and even global, for example, changes to circulation patterns. And for ACI, it's highly uncertain. For MCB, it's completely unknown. ACI is uncontroversial. We've lived with it from the beginning of the industrial age. MCB is highly controversial, and its effects are really completely unknown. Just a few differences between ACI and MCB. So the key of this roadmap is that we provide 6 checkpoints, and a checkpoint is defined here as a key topical area with open questions that must be resolved before a solar climate intervention method can be considered viable. And what are those 6 checkpoints? They start with the smallest scales of generating particles and delivering them to the clouds. The second checkpoint would be local cloud adjustments. And by this, I mean the liquid water path changes. So we can't just think about this as a to-me brightening. We need to think about potential offsetting effects like liquid water path adjustments. The third checkpoint is the scale of susceptible clouds. How frequently and over what areas, aerial coverage, do we have clouds that are susceptible to particles? The fourth, signal detection. If we do intervene, if we do inject particles, would we be able to detect those signals? The fifth, and where you can see we're going up in scale over here, gets to the marine ecosystem impacts. To what extent would we influence marine ecosystems by generating large quantities of salt particles in the marine boundary layer? And finally, and no less important, if we are to seed a large area, perhaps in the Northeast Pacific or some other large stratocumulus deck, what might be the large-scale circulation responses? Would we be influencing the regional precipitation, for example, in some part of the world? And key to this is that all checkpoints in our mind should be studied simultaneously. Even though I'm displaying it here as a roadmap, these checkpoints should be studied simultaneously and continually revisited. And all checkpoints must be passed. And we should exit the research program if these key uncertainties cannot be resolved. So this is what I meant by kind of self-governance in the absence of a national or international governance program. Importantly, this roadmap paper does not advocate for marine cloud brightening. It's agnostic. It's really trying to understand the problems, the issues, and present the results of our findings ultimately to decision makers. Another important aspect is that the physical science cannot be separated from other important aspects. I won't go into it here, but we need to think about technology, ecology, social science, and ethics. And this is where it gets quite complicated because we all have our strong feelings about marine cloud brightening. So a couple of weeks ago, there was a joint NOAA and DOE ASR workshop on MCB. There were about 30 participants, including some present in this meeting from different walks of life. There was rigorous discussion of the physical science issues. People came from a mix of backgrounds, early, mid-career, senior, and had a range of skills, looking at a range of scales, of the range of tools, models, observations, and lab experimental work. Key questions that we addressed: what do we know and what are the main knowledge gaps? What are novel ways to address those gaps? What are the biggest challenges? And what are the must-haves for an MCB research program? What must we know before we can even proceed to think about actual experiments in the real world? I'll summarize then. The MCB is under serious consideration by various international bodies, and it's our responsibility, therefore, to provide the best information we can to decision makers. We have developed a roadmap with 6 physical science checkpoints and exit ramps. All these checkpoints should be passed for a viable MCB program. We should exit if key uncertainties cannot be resolved. We do need to consider technology, ecology, social science, and ethics in addition to the physical science that we've addressed in this opinion piece. And we don't advocate for MCB. This is really, this work is agnostic. It's trying to provide the best factual information. And then just finally, NOAA and DOE recently convened a workshop to discuss the issues, and a report and paper will follow. Thanks.
Thank you, Graham. We're on time. We have time for one quick question. Zenking, do you have your hand up? If you'd like to unmute yourself and ask a question, that would be great. I think
Can't hear you, Zenking.
You're muted.
You're not muted, but we can't hear you.
You could try to type your question into the chat. Okay, we're unable to hear you, so I'll read a question from the chat. Oh.
Can I ask a question?
Oh, sure, Mingwei.
Yeah, so I think just a quick question. So it's a relevance for us. So like, I think you need the 6 points. That's I think that's cover a lot of the different aspects. So like for us at the ACPC, do you see any particular rule or any like initiatives should we put forward like to support this as a community efforts?
Well, I think clearly our expertise comes in under the checkpoints of generation, delivery, scale of susceptible clouds, and adjustments. Of course, we could extend that to questions associated with detection for those amongst us who are involved more in the looking at the radiative effects, you know, through platforms like Ceres, instruments like Ceres. But really, our expertise, I think, comes in under those first 3 checkpoints, and all the work that we do, to some extent, helps with those particular issues. So in my opinion, we just keep doing what we're doing. We could have an eye towards MCB as it becomes discussed more and more, and as governments start sending funding in our direction.
Okay, thank you.
Great, thank you, Graham. And there's a few more questions in the chat if you'd like to address those afterwards. For our next speaker, we'll have Vela Toll discuss temporal evolution of polluted cloud tracks. Vela, are you here?
Yeah, thanks, Matt. So if Graham stops the sharing.
Sorry, no.
Okay, good. Here we go. So the title changed a little. So I would like to discuss how to use polluted cloud tracks to better constrain radiative forcing. So polluted cloud tracks, most of you know, these are ship track-like perturbations over land. And what's good about these industrial aerosol sources inducing these tracks is that these are continuously emitting mostly, or the sources that we study at least, and these are at fixed locations compared to the ships. So why I think these tracks are very important for radiative forcing is that similarly to tracks, there are these large-scale cloud perturbations, like here, downwind of China and in Great Lakes region, US, where these bright regions are areas with increased cloud droplet number concentrations. So it seems to be that the meteorological dependence of the occurrence of this large-scale, very strong increases in cloud droplet number concentrations is rather similar to tracks. So here you can see this large-scale polluted area, but here you can see also the tracks. Our feeling is that these large-scale strong perturbations could cause rather strong forcing. So what we have done, we have studied the conditions where we get the tracks, the conditions where there seem to be suitable clouds for track formation, so liquid, warm clouds, but no tracks, and then also conditions where we don't have clouds, or we have ice phase or mixed phase clouds, not liquid warm clouds. These conditions are quite special where the tracks form. So here is for one mid-latitude site, here is climatological circulation types. So this is not just wind direction, this is kind of large-scale flow-based circulation types here, and cyclonic, anticyclonic are not shown here. But this is climatological, and this is for track favoring conditions. So for track favoring, we see a clear clockwise shift, and also it's anticyclonic conditions what mostly favor this strong anthropogenic cloud perturbations over land at least. So this is the large scale kind of control, but of course there's kind of many different parameters, conditions what affect the track formation. And I mean, we have sampled this for a few locations, and we have some clear signals here. For example, tracks tend to form more in thinner clouds, in less polluted clouds, in case of lower relative humidity, but not in all cases the physical reasoning is that clear. But still, I think if we now are building these large databases of tracks, so we will see 2 or 3 presentations presenting machine learning detecting these tracks and having these large global databases, I think this can be useful in forming the radiative forcing estimates. For example, such nice observations-based sulfate to cloud droplet number concentration perturbation, but also considering the meteorological dependence, and perhaps tracks can be useful here if it is reasonable representative or it is large enough database. Another aspect, so far this ship tracks and ship track-like perturbations, most studies and most of our studies as well have focused on these net responses in tracks like the albedo changes, for example. And yes, we have seen, for example, this kind of responses where increases and decreases in cloud water seem to be compensating each other. But so far we have been unable to confidently say that why is that? What are the reasons for the increases in cloud water? What are the reasons for the decreases? So one solution could be the temporal evolution. If we can have like kind of a time series of these tracks, then this could provide some answers. So we tested this using severe data, sampling these tracks during daylight hours every 15 minutes. But well, the results are not that good, or I mean, we don't have any confident answers based on that. So we do see increases in cloud water in the afternoon in some cases, and gradual increases in some cases. But regarding decreases in cloud water, these already occur since the early morning, and we don't see really during daylight hours gradual decrease in cloud water. So perhaps decrease happens during nighttime, perhaps there's some retrieval bias. So it's not a very clear result what we got from the severe data. But of course, we need to consider that here the spatial resolution, it's just 10 kilometers or so for the European part of Russia. And it's much more noisy compared to the MODIS data, for example. So what could help, we plan to use this ABI data, what's higher spatial resolution, but perhaps it could be possible to sample some interesting region using some dedicated geostationary scanning strategy. I mean, Meteosat, the 3rd generation about to be launched, or for ABI, I'm not sure, but perhaps it is a possibility to do that kind of stuff. Another thing what would be super nice is to have some kind of mobile facility, like atmospheric radiation measurement mobile facility at the location of frequent track formation to sample these clouds and get some much more detailed physical understanding of these cases. So yeah, I mean, really to make progress based on these polluted cloud tracks, I mean, I think we need to move forward from this studying the net responses or just albedo response and really try to get more physical understanding out of these tracks. But we're now having these obstacles. What kind of data do we have available to do that? Thank you.
Thank you, Vela. That was a great talk. I actually have a quick question. In some of these land locations where you quantified the frequency of occurrence, I was curious if you also looked at the vertical soundings of temperature and humidity to see whether decoupling near the surface might prevent the pollutants from reaching the clouds on these days where you see favorable cloud conditions, but maybe there's a subcloud inversion. Have you looked at sort of vertical soundings from balloons?
Yeah, so we didn't really look at the soundings, but regarding the coupling and stability, I mean, we saw that in extreme stability, in case of extreme stability, the tracks did not form as the pollution did not reach the clouds. I mean, we know that very stable conditions are favorable for strong perturbations, but what was interesting that under extreme stability, these anthropogenic cloud perturbations do not occur. But yeah, it's. I mean, we tried to analyze that. Could it be kind of a surface-mediated control there, but we didn't see very clear signals based on some indirect parameters what could kind of reflect coupling, decoupling. So it is expected, but we didn't see very clear signal in our preliminary kind of analysis.
Thanks. Ming-Wai, do you have a quick question?
Yes, very nice talk. So I have a question for the source data. It seems to me, your results show a clear enhancement of liquid path, right? You said in the afternoon, but then you said it seems the results are still not strong enough or clear enough, especially compared to your previous results, because the previous results suggest the relative liquid path response, but the source data seems to suggest. I think to me it's pretty evident enhancement in liquid path. So how to reconcile this two results? Also, you mentioned the resolution. So is that because of resolution or there's something else going on? Thank you.
Yeah, thanks. So this was Severi on the Meteosat second generation. So yeah, it's. I mean, nobody has really used Severi data or geostationary data in that way. So our first task was to kind of check if we can use geostationary data in a quantitative manner for that kind of a narrow tracks. But yeah, we think it's a combination of kind of spatial resolution, but also spectral resolution or the ability of I mean, it's a similar algorithm, of course, as for the MODIS cloud optical properties, but I mean, it's different spectral resolution and there are some differences. So we're not very convinced at the moment in the quality of the Severi data. So I think we need to do much more extensive quality control in the first place to say if we can trust these results or to what extent we can trust these. Thanks.
Okay, thank you.
Great, thank you, Vela. So now we will move on to Daniel Grosvenor's talk, High Resolution Simulations of Hawaiian Volcanic Emissions Interacting with Clouds Reveal a Strong Role for Island Orography. Take it away.
Okay, hi. Yeah, so I'm not going to talk a little bit about orography, but maybe not as much as I made out. So this is cloud resolving simulations of the Kilauea volcanic eruption. It's work in collaboration with Polfield and others there. Okay, so the Hawaiian volcano, we think is quite a nice case study to study aerosol cloud interactions. That's because a lot of the aerosol effects are quite local to the region compared to, for example, the volcanoes in Iceland that have been studied before, that we've studied before, where the aerosol tends to get transported further afield and the cloud effects are much further afield due to the long-range transport and getting the aerosol getting into the free troposphere, for example. And for Hawaii, they're mostly boundary layer clouds, trade cumulus, liquid clouds, compared to Iceland, where in the North Atlantic, where we've got lots of overlying ice clouds and frontal systems and more complicated clouds. We've also got fairly consistent wind conditions and cloud conditions. So for those reasons, we think it's quite a nice study. We're studying this eruption from Kilauea in December 2020. This is just the SO2 emission rate measured using an upward pointing ultraviolet spectrometer. So you can see we had high emissions for the first 6-7 days, and then it's tailed off to a fairly steady state of low SO2 emissions. And we're looking at the first 4 days of the eruption here in the simulation. So we're using the Met Office unified model with the UKCA aerosol chemistry scheme. So that deals with all the processing of the SO2 into sulfuric acid gas and then conversion into aerosol particles. And also deals with the aerosol side using GlowMap. So we've got quite a sophisticated chemistry and aerosol scheme. And then we've also got the Kazim cloud microphysics scheme. So that's a 2-moment scheme, which is replacing the older microphysics, which only had a single moment. So we might expect, for example, we might expect that to give different rain rates, for example, which is important for aerosol cloud interactions. So we're using this at 4-kilometer resolution in nested mode. So it's cloud resolving, but I guess importantly at 4 kilometers, we don't need to use the convective parameterization, which doesn't respond to aerosol. So we don't want to use that because then we won't see any aerosol cloud effects. So yeah, so these are the simulations I'm doing, I guess. The volcano on and volcano off experiments for these 3 different runs. We've got orography on and orography off because we're interested in the effect of the orographic wake on the cloud field, which could confuse matters when looking at trying to find the aerosol cloud interactions. I've also done a run with no aerosol direct radiative effect. So I'll say a little bit about that. So at 4-kilometer resolution, 4 days, we're emitting SO2 between the surface and 3,000 meters. Yes, this is just a quick snapshot of the MODIS cloud field in the visible, just shortly after the eruption, and the model liquid water path at the same time. So you can see we've got lots of small scale trade-cumulus type clouds, lots of cloud-free areas, especially downwind of the orography of the volcano mountain, and also some thicker, more organized clouds, which we see similar things in the model, and some clear sky downwind of the mountains, and then a fairly similar trade-cumulus. But we need to do obviously a more quantitative analysis there. This is just a quick look, so I haven't done that yet, I'm afraid. This is volcano on minus volcano off values for SO2 on the left, so vertically integrated SO2, and vertically average droplet number concentration on the right. So you can see a plume of SO2 coming off the mountain towards the southwest, and a corresponding increase in droplet numbers with values up to over 300, increase by 300 or more, and then less downwind around 100 or so. And here we're just looking at the volcano on minus volcano off cloud macrophysical changes, so the adjustments. So we've got changes in the liquid water path in the cloudy sky only. So in cloud liquid water path on the left, and changes in cloud fraction on the right. Orography on top row, orography off in the bottom row. So you can see the change in liquid water path is kind of variable, positives and negatives, a bit noisy, whereas we have a clear decrease in cloud fraction, which was a bit of a surprise to us. So with more aerosols from the volcano, we're getting a decrease in cloud fraction. And orography on and orography off, you can't maybe can't see too much change here. There are actually changes close to the mountain, just downwind. But I guess the message would be if you focus further away, then the two orography doesn't make too much difference as long as you're far enough downwind. But yeah, but this big decrease in cloud fraction was the interesting thing, I guess. These are just some PDFs. Again, volcano off, volcano on, volcano off in blue. So droplet numbers, you can see a clear increase in droplet number, and these are the mean values. So going from 26 to 120. Here I'm focusing on the high SO2 regions, so kind of where the volcano was influencing things. Liquid water path here in the middle, you can see a slight decrease when we switch on the volcano. So more low values, fewer high values. Similarly for cloud fraction, but maybe a bigger change. And the rain rates are also affected, which is usually the main mechanism for aerosol cloud interactions for adjustments. So with volcano on, we get smaller rain rates, as we might expect. So yeah, so this decrease in cloud fraction is perhaps a bit strange, a bit unexpected. I guess we would note that these are trade cumulus type clouds, or maybe more organized, deeper clouds compared to stratocumulus, where maybe at least I'm used to more thinking about more. I should note that it's not the reason for this decrease in cloud fraction in liquid water path is not due to smaller droplets causing more entrainment, because this is not in the model right now. But it will be good to develop this, maybe using some of the observations of entrainment that we saw yesterday. And it's not due to aerosol direct radiative effects, because we switch those off and we still get the same result. I'm not showing that, but I'll just take my word for it. Looking at the ERFs, so we calculated those. So we've got ERF ARI, the direct effect, and the aerosol cloud interaction ERF. And we can see the ARI is actually much bigger than the ACI. So we've got a big negative direct effect, quite a small negative ACI. And I'll split the ACI ERF into contributions from liquid water path changes, cloud fraction changes, and droplet number changes using an offline radiative code. So you can see here we've got a negative cooling due to Trumie effect, as we might expect, but we've got these offsetting contributions from cloud fraction and liquid water path changes. And that's what's leading to a more muted ERF ACI. This is just a map of the ARI, ERF ARI on the left and ACI on the right, just highlighting that the ACI is quite noisy and ARI is strong, high magnitude, and more consistent. So maybe maybe it shouldn't be too much of a surprise, because the cloud fractions here are generally quite low. This is the time mean cloud fraction. And we can see, well, I guess it's more of a wake effect, but we can see low values around 0.4, 0.5, getting maybe down to 0.2. So there's quite a lot of clear sky, which maybe helps with the ARI, but still a bit of a surprise to us that the ARI was so strong. So wrong way. And one more thing we've been doing is just trying to, I guess, evaluate the model rain rates in some way, because we saw this paper by Murakami where they had these 2D histograms of rain rate on the y-axis and liquid water path divided by droplet number on the x-axis. So that's, I guess, akin to droplet size or similar. And so yeah, we're just doing a qualitative comparison here, but this is the same from the model, and we get a similar shape. And the black line is the result from Comstock using radar, and these results were from satellite, I believe. So we need to do a more quantitative analysis of this, but I guess the kind of general shape of the PDFs is similar. And yeah, so that brings me to conclusions. So we see when we have switched the volcano on, we see a large increase in cloud droplet number, but that leads to a decrease in liquid water path and cloud fraction, more so in cloud fraction. And that's kind of opposite to what we might expect from the suppression of rain by aerosols. So we're still scratching your heads, trying to look into the mechanisms for this in the model. And also we saw a bigger ARI effect compared to ACI effects. So maybe what I said about in the beginning about this being a good case study for ACI is perhaps not true. Maybe it's a better case study for ARIs. We think that's maybe because we've got low cloud fractions in this region. And yeah, I guess it's quite interesting to see some of the entrainment observations yesterday. And maybe if there's more observations looking at rain rates, we could do similar evaluations in the model. And yeah, in the future, we'd like to do more quantitative comparison using satellite data. So with that, I'll end the talk and take any questions.
Great, thank you. We have, let's see. Oh, Andrew asked, does the season matter? For example, December, it might have fewer clouds.
Possibly. I've not looked at the different seasons, I guess. We just kind of picked this eruption, but yeah. Yeah, it seems like well, I guess different seasons you might get different regimes, but which is interesting in itself, whether different regimes have different responses to aerosols. But we're not looked into that, really.
Are there any other questions? Do you have any ideas for what you might test next for to further understand the positive liquid water path and cloud fraction responses?
Well, we had a look at cloud top height, and they were quite similar between volcano on and volcano off. Now, there's no ice involved, or very little ice forming. So yeah, maybe we should look at vertical velocities, or I guess it could be something to do with cold pools or organization. Yeah, we need to, some ideas, but we need to, I don't know, open to suggestions.
Yeah, I'm seeing some similar results in a different island location with positive liquid water path and cloud fraction responses. So yeah, be curious to hear more about that. But all right, great. Well, I think we can maybe move on to the next speaker now. Duncan, are you able to share your slides?
Yeah, 1 second.
This will be on shipping regulations lead to large reduction in cloud perturbations.
Great, thank you very much, Matt and Andrew. Yeah, so this is, yeah, exactly. So I'm going to talk about how we've detected these changes in perturbations. I don't really need to do this slide, but the aerosol forcing is obviously still one of the most uncertain aspects of the climate system. This is just an updated plot of one we're all familiar with from AR6, and ACI still stands out as a key uncertainty, and this obviously contributes to uncertainty in present day temperature change and even in future projections. Matt and Andrew and many of the people here were involved in this really nice review paper which described the ways that various different opportunistic experiments can help shed light on these interactions, and Fella really nicely outlined some of the ways that he and others are looking into industry tracks and what they can tell us about both microphysical and then bring that up to regional scale perturbations to the climate system. In this particular talk, I'm going to be talking about the effect of shipping, and in particular ship tracks, which many of you know much about, and Graham already introduced quite nicely in the first talk, so I won't dwell on it, except just to reiterate that these perturbations, these phenomena are an important indication of ACI in a useful laboratory, but remain arduous to detect and catalogue, and that means that most research on this tends to still use fairly limited data sets in terms of either spatial scale or temporal kind of catalog, I guess. And so in this work, we train a machine learning algorithm using those previous data sets, those previous hand-logged data sets, both in the Northwest Pacific, Northeast Pacific, and South Atlantic and South Pacific as well. Paper from Segrin, and also some tracks from Vela and others, and a lot of work from Matt and Ed as well, bringing these hand-logged tracks together. And in total, we had around 5,500 tracks, so a similar number of MODIS scenes across different regions and across different seasons to give us a pretty broad set of training data with which we could then train a machine learning algorithm to go and find these for us automatically. And so what does that look like? So we take microphysical composites from MODIS, near infrared, visible, and IR channels, and turn these hand-logged ship tracks, which I've just outlined, into a bit mask, which we use to highlight the regions of this image which are the ship tracks that we're interested in. And we basically have, as I say, we split the whole MODIS scene up. So we retain the 1 kilometer resolution of MODIS, but we split the swath up into roughly 400 by 400 kilometer tiles, and ask the algorithm, train the algorithm to go and find these similar features in the rest of the data set. Now, this image on the right is a held back test image. So we didn't show this to the model during training, but then asked after the fact, where do you see the ship tracks? And you see it does a really good job here of finding out these narrow features. And there's another slightly more interesting example here with numerous ship tracks intersecting across different clouds. Again, the algorithm does a really good job of picking out tracks that are definitely tracks, and B, ignoring regions and linear features that might otherwise trick it or fool it into thinking it's a track. We did a various, exploration of the various different parameters and hyperparameters which you can choose when setting up these kind of models. So there's different aspects that you can tune in order to increase the precision or kind of essentially limit the number of false positives and make sure you get the best number of true positives. And we found a model that we, as you see here, we're pretty happy with and does a really good job. Now, the next trick is to actually run that model, and MODIS imagery at that kind of resolution is pretty heavy. So it's about 20 petabytes of raw imagery that we had to kind of apply this model to, so while we're not sitting there hand logging it, it's still a kind of fairly heavy effort from computationally speaking. So we created the subset of these composite PNGs, tiled them up, and that gets you down to about 250 terabytes of data, which we were able to process down the road here in the UK at a new machine learning cluster. So they have a cluster of GPUs we were able to use, which churned through this in about a week, 5 days or so, and produced these masks, which I described before. So these bit masks, which are where the machine learning model indicates that there's a ship track or not. And then we can pull out polygons representing the actual tracks themselves in a kind of more useful data set for analysis, which we will put on the cloud as soon as this paper is out. And that's kind of more manageable, about 40 gigabytes or so. And in total, having applied that model then to the whole of of MODIS Aqua for full mission for about 20 years, we found over 1 million ship tracks around the world. There were hotspots off the coast of California, which is not entirely surprising. That's obviously a region which has been heavily studied before because that stands out as having a lot of these ship tracks. Similarly, in the Southeast Atlantic, a few in the North Atlantic, and a few interesting spots as well. So we found quite a few in the South Australian Bight, which was perhaps a bit less expected. We found a few around Indonesia as well, which we're not entirely sure are potentially volcano tracks because they're a bit more spatially localized, but we're still looking into that. But the really nice thing we can do now is then look at a time series of these global tracks, and particularly with reference to the change in emissions that occurred in 2020. So this is for the full mission, excluding 2002, which didn't have a full year of retrievals. And you find that globally, we find around 35 to 40,000 ship tracks a year. And you can see as the emissions, this is in red, is the global emissions from shipping, that took a very sharp drop due to the regulations which were introduced in 2020. So the IMO restricted the amount of sulfur that ships were allowed to burn in the open sea. And that has had a clear and pretty stark effect on the prevalence of ship tracks globally. And if you look at the different regions, this effect has happened pretty much equally across the globe, and we'll dig into that a little bit in the following couple of slides. I just want to point out that this stark change in ship tracks doesn't really stand out if you look at similar scale, other cloud features at a similar scale. So if you just look at MODIS ND, for example, in the global mean, over the same period, you see this trend in the global mean value, but you don't see any dramatic drop over the last 2 years. Similarly, even regionally, you don't see this in the North Pacific or the South Pacific. You could maybe convince yourself that you see a drop in the Southeast Atlantic, but it's still just about within the variability. So if we dig into where these changes occurred. So here I'm actually showing a map of the change in ship tracks that occurred due to the near coast regulations change in 2015. So this was a kind of precursor to the full global emissions restraints that were brought in, and they just occurred around the coast of North America and Europe. And you can see a really clear reduction in the number of ship tracks in this Californian economic zone. I've got a kind of blow up of that region here, and it really follows this this Sika zone very nicely. And you even see a bit of an increase outside this zone as ships recalibrate their routes to go around it. And Ed showed this in his paper to some extent in 2019, but this with more data we can show this really clearly. Now looking at this global change in 2020, you can see that this reduction is much more uniform across the globe. In fact, there's perhaps a slight increase inside the Sika, as now those ships don't, there's no price differential for going inside or outside, but otherwise it's a very broad reduction everywhere. In this slide, I wanted to just highlight the how closely the ship tracks follow the shipping corridor in the Southeast Atlantic. And this really nicely kind of justifies, if you like, Michael's analysis that he did along this track, along this corridor. And again, you can see that the change in ship tracks in this region is very, very clear. I see I'm running out of time, so I'll just quickly point out the sensitivity to emissions that we can calculate using this effect, sensitivity of ship tracks to emissions. You see a large sensitivity in the North Pacific, particularly in high cloud fraction clouds. I'll briefly trail some future work, particularly with respect to what Bella was saying, where we apply this model to geostationary data combined with high resolution ship locations, and we can dig a lot more into that. And this, I think, hopefully tees up Peter's talk, which is coming up in the next slot as well. So just very briefly to summarize, obviously we applied this machine learning approach to 1 kilometer MODIS imagery and found more than 1 million ship tracks over the 20-year period of Aqua. We see a 25% drop in ship tracks pretty much everywhere after this emissions change. And one thing I'd like to just kind of point out is that this signal is not a linear reduction, right? There was an 80% reduction in emissions, and we only see a 25% reduction in ship tracks. And this potentially speaks to the difficulty in finding pristine regions in which to perform marine cloud brightening. So I'll leave you with that and happy to take any questions.
Great, thanks, Duncan. Any questions?
Duncan, this is Graham. Very nice, really nicely presented and nicely done. There's a lot of talk about undetected ship tracks and the fact that they may be contributing even small amounts, but over large areas. Could you speak to the possibility that these undetected tracks are just not making it into your analysis, and whether there might be enough of them to have some radiative effect?
That's a really good question. It's certainly possible that they're not accounted for in this data set. I mean, it's trained using the same kind of visual identification that a human would. So there's nothing kind of special in that regard. So it would be missing those. I'll again just flag Peter's talk, who I think is coming up next, who has a really nice technique for finding these invisible ship tracks. And he'll present some of the results from that.
Thanks.
In the essence of time, I think maybe we should move on. Vela, if you had a question, maybe type it into the chat. And so thank you, Duncan. And our next speaker is Tianli Yuan. Are you here?
Yeah, I'm here. Hi, Matt.
Okay, great. So this talk will be observational evidence of strong forcing from aerosol effect on low cloud coverage. Take it away.
So continue on the theme of ship tracks. This study is with a group of scientists listed here. We are looking at how clouds respond to ship-emitted aerosols within ship tracks. Of course, this is following a long line of studies doing this kind of work. Duncan just gave a nice introduction to this, so I'll skip some of these. You know this paper, many of us are on this. And very similar to what Duncan was showing, we developed our own algorithm to detect this kind of ship tracks within MODIS image. And this paper outlines the details of this algorithm. And actually, we looked at really similar stuff, what Duncan just reported, and the agreement seems to be pretty good. So we are seeing similar things. And so once we have this detection, for example, on the left side, I'm showing two cases. The original MODIS image is on the right side, and this is the detected ship track mask overlaying this like pinkish color overlaying on the ship tracks, showing that the model can do a pretty good job at picking out the ship tracks under quite complicated situations. And so once these ship tracks are detected, we also developed an algorithm to automatically analyze these ship tracks by comparing the red ship track and their neighbors with some separation in between. Because as we know, sometimes the boundary is pretty hard to exactly pin down. So once we have that, we can analyze a bunch of ship track examples. So here I'm showing kind of a similar map with what Duncan just showed. This is the climatological ship track densities. So that's relative to low clouds. And overlaying is the ship emitted SO2. Also, so this is coming from which emission data set I forgot. So one of the emission data sets. So you can see the shipping corridors being detected. So we did a quick and dirty calculation. So if we follow the sort of the criteria in Valley's paper, this is equivalent to about 12 million ship track segments in their paper. So that's quite a bit of samples. So in terms of cloud response, the bulk adjustment is the PDFs are shown here. So as expected, effective radius is going down. The mean value of standard deviation skewness are listed in each plot. The mean LWP is actually increased by a little bit, but with huge standard deviation, in other words, huge variability. This is also agreeing with Bailey and many other people's work, but the mean value is slight positive and the skewness is towards to the increased side, although you have almost equal chances of getting decreases. In terms of cloud fraction, the mean increase is about 9% for all the ship track samples. Standard deviation is also quite large. This is because we'll show next in the next slides. So in terms of how the liquid path adjustment depends on, say, background conditions. So we kind of followed previous studies and looking at the background number concentration, background cloud effective radius, and background cloud, say, above cloud relative humidity. So we get these curves. For example, the number concentration, as we get more polluted, the liquid water path response to increasing number concentration tend to decrease the liquid water path, and vice versa. And the above cloud humidity tends to also has a negative effect if it's dry above cloud. And this is kind of little new results, and this is looking at cloud fraction sensitivity to the number concentration within ship tracks. And for majority of clouds that's sitting here, so if we're looking at follow the green line, which is background effective radius, relatively polluted clouds, the effect of cloud fraction doesn't show much change at all. But once the effective radius is larger than 14 micron, which Danny showed in their paper a few years ago, that means appreciable precipitation is present. And once the clouds in that condition, the cloud fraction tends to increase strongly with number concentration. And the cleaner it is, the stronger increase. And so we had one data point from simulations, which is Posner et al. In 2018. They simulated a condition under which I think it's around 10 per cc in terms of number concentration, and their cloud fraction response, the sensitivity is quite similar to what we found in our observational study. Of course, previously we had a lot of studies documenting the ship cloud fraction increase in response to these ship tracks. So then, without going into too much details, we can use these relationships and its dependence on the background to come up with this kind of forcing estimates. And we can see this two effect still dominates over the global ocean, but the liquid path, even though the color shows it's kind of warm color, but mostly it's actually a slightly negative. It's just because of the color scheme. But the cloud fraction effects, so this of course will depend on the assumptions we make. Conservatively, it will represent about 60% of the Toomey effect. So that's a big component. And if we using different assumptions, we can get as much as 100% or 200% of the Toomey effect. So it has great potential. So I think a lot of uncertainty in our estimate of cloud aerosol indirect forcing in low clouds is coming from this effect. So a bit of cautionary, some cautions about these. So sampling is really important, we found. So for example, everyone remembers Valley's paper in Nature. So we found that if applying different filters towards these ship track samples have big effects on both PDFs and the cloud response you get. For example, these are applying two separate filters, both reasonable, but if you look at the liquid water path response, we get quite a big difference. And it also, of course, it has the dependence on the cloud regimes. Under different cloud regimes, we see direct observations from series show that the cloud albedo change observed in these ship tracks has clear dependence on the cloud regime, underneath cloud regime. So for some cloud types, this is mesoscale regimes, the albedo change is much stronger than others, say, if you compare these two. And I think my time is up, almost up. So I'll leave the conclusions here and take questions if I have time.
Great, thank you. Bella, do you have a question?
Thanks, great work. So the question I always get for these tracks that this forcing estimates that these are great, but how representative are these tracks, and how much we can trust anything we tell about forcing. So this is very interesting that you see this dependence on the data screening or this thresholds, that how strong is the cloud droplet number concentration perturbation. So do you think you could use that kind of sensitivity to tell something that do strong perturbations behave similarly to weak perturbations, etc.?
Right, great question. As you probably know, like if you compare like continental with ship tracks, you will find different things too. Yeah, so it actually has implications for many things. So this dependence, first of all, in terms of representativeness, we sort of, when we calculate the forces, we used, say, background effective radius, or we use the number concentration. And you can pile on, like if you want to include environmental conditions like stability or humidity, above cloud humidity, then you probably get some slightly different results. So it is quite complicated in that aspect. And for this, yeah, so I think the message is going back to the ship track detection, once you have different thresholds or emissions from ships, you tend to detect different kind of clouds. So that also plays into it. I can't like summarize a single point. It's a complicated problem. I think we need to do more analysis on this.
Great.
I know
Thank you.
I didn't answer your question clearly.
Thank you for the presentation. That was great. I think in the essence of time, we'll move to our next speaker. So we're going to now pivot from the visible to the invisible for ship tracks. And Peter will be discussing invisible ship tracks as opportunistic experiments for aerosol cloud interactions.
Thanks, Matt. First, can you hear me all right?
Yes.
Cool. I'll try to share my slides. And now can you see that all right?
Yep, looks good.
All right, thanks. So yeah, I'm gonna discuss some work that I did on invisible ship tracks. So this links up quite well with the previous talks. And this was in collaboration with Duncan and Matt and Jukka-Pekka Jalkanen and Philip Steer. And yeah, just as a again a nice picture of ship tracks, like in the previous slides, just to remind ourselves of what they look like. But precisely in this work, I was not interested in these beautiful like linear cloud features, in this case off the coast of California, but rather in the large amount of well, invisible ship tracks, so the cloud perturbations that we cannot see in a satellite image like this. So it's estimated that only a fraction of the shipping perturbations actually cause tracks that are visible in satellite images like this. And so it's interesting to try and find the perturbations kind of independently of these visible tracks. So what we did in this study was using the emissions and the positions of ships from the automatic identification system. So you get ship positions over that time resolved, and they look something like this, like these boxes on this plot. And then if you then combine this with reanalysis data of winds and advect those emissions with a high split model, then you can get actually quite good collocation, or you can see that these emissions end up more or less where we also see those visible tracks. And then you can collocate this with the modus retrievals of cloud properties. So in this case, in this image, for example, the effective radius, and then compare with a counterfactual to either side. And now the interesting thing about this is that we can not only do this on days when there are tracks like we saw in the previous picture, but also on days when we cannot see any of those. So this is like an example day when we have ships passing through this region, but there's no visible tracks actually. And the interesting thing about this is that when we average over several days of observations and several of these tracks, then we can actually get some signal in cloud properties. So dividing into the two kinds of images you've seen on the previous slides, so the days with visible tracks and without visible tracks, and just analyzing the days separately, and in the same region as before, you can see in the top plot, if we compare the in track and the out of track droplet number concentration, that in the case of the visible track days, as we expect, we get this time resolved increase in droplet number concentration, which goes up, which peaks around 4 or 5 hours, and then goes down over the scale of a day. And we also see that increase, or at least this shape, with a slightly smaller amplitude for the invisible case. So on days when actually visibly or like visually we can't identify any ship tracks. Looking at the liquid water path, we can also see that the response here is different in both cases, and this is quite interesting because actually the response in the invisible case is of different sign from the visible case. So we seem to have an increase in the liquid water response. Now, comparing the meteorology on the different days to try and answer the question why some of those days display visible tracks and others don't, we collocate this to ERA 5 data and find that the visible tracks occur in more stable boundary layers. They also occur in shallower boundary layers over colder sea surface temperatures and at higher relative humidities. Now, so far we've looked at this region here of the in the Southeast Pacific, but extending this data to this box, we mainly actually had lots of data of the Atlantic and looked in particular at these 3 additional regions. And we can see that in the droplet number concentration response, we have also a strong response in the other stratocumulus deck here off the coast of Namibia. But we also see smaller increases in these 2 regions that are on here. Now, interestingly, even though the droplet number concentration changes are different, the albedo changes seem to be of quite similar magnitude, comparing all of those regions. And this is because the liquid water changes are actually stronger or more positive in these 2 boxes. And so the lower droplet number change seems to be compensated for by the more positive liquid water change. Now we can do this also kind of more like a heat map. And here again on the left, we have the droplet number anomaly, which is strongest in these 2 stratocumulus regions. But then the liquid water anomaly actually is strongest in these trade wind cumulus regions here. Now, trying to answer why that is, we can compare to 2 things, both the background droplet number concentration, so that's this plot, and we can clearly see these two stratocumulus regions where droplet number concentrations are very large, and this also coincides with high inversion strengths, so rather stable atmospheres. Now, because the liquid-water path ND relationship is nonlinear, and we've seen this before in previous talks as well, it makes sense that in the lower droplet number concentration regions, we get a more positive liquid-water path response. But also another process here may be the fact that in regions where there's a strong inversion, actually there can be no, the cloud will not be able to deepen. Whereas in regions where the inversion is not so strong, clouds can deepen, and because the liquid water path is a function of the geometric thickness, we will get an increased measure of liquid water. Now, trying to do a forcing estimate from this globally, we can try to do this because we're limited to this box that I showed before. We can try to do this by extrapolating the sensitivity that we find to the whole world using the EIS and viewing the sensitivity as a function of EIS. So that gives us this kind of extrapolation where we see that these stratocumulus regions have this low sensitivity, and we see those stronger sensitivities in the regions with which are more unstable. And multiplying this with anthropogenic droplet number concentrations and cloud fractions, we arrive at a remarkably strong cooling effect of the rapid adjustment of liquid water of between -0.5 and 1 watt per meter squared in the global average. So that's very much and very cooling, especially compared to the IPCC estimate, which is between 0 and positive 0.4 watts per meter squared. Now, just to summarize, this study has relied on the location of emissions rather than on visually identifying ship tracks, and that allows to study all of these regions and all of these cloud types. On the days of invisible tracks, we can still detect tracks, and their liquid water response seems to be different. And we can also detect them in these trade wind cumulus regions where also the liquid water response seems to be different. And this all points to the question whether previous ship track studies have suffered from a selection bias by only focusing on visible tracks. And that's it for me. Happy to take any questions.
Thanks, great presentation. Do we have any questions? Tianli, do you have your hand raised?
Yeah, Peter, that's a great talk. So I missed the first bullet point you listed here. You rely on emission locations. So do you like track each ship's location? Is that how you do it?
Yeah, so they actually do that themselves. There's a system called the automatic identification system.
Yeah.
I think every ship has it, and they log their geographic positions.
Right.
I think hourly.
Do you select? Yeah, I know those AIS data. So you propagate those locations using ERA wind, and do you filter out any ships or just include everything?
So we had like a little look at whether it makes a difference to look for different to basically try and differentiate by emission amounts, but it did not make as big of a difference. So we decided to just include all of them.
Ah, I see.
And you can also see actually, I mean, the data set is not necessarily complete. So on the first plot here up there, you see that there's actually nothing corresponding to that big track-like, track here in the middle. So that the data set probably does have some gaps of ships that don't have their AIS data logged.
Right. Yeah. Thanks.
All right, great. We have a few questions in the chat, Peter. Maybe you might address that are
Sure.
related to liquid water path and ND changes that are quite interesting. But I think in the essence of time, we'll move to the next speaker. But thank you very much.
Sure.
So our next speaker is Ed Greisbeard, and it is short timescale cloud development to constrain aerosol cloud interactions in liquid clouds.
Hi, Matt. Can you hear me?
Yes, loud and clear.
Yeah, okay, great. Good. Is that working now? It says I'm sharing.
Yep.
Excellent.
Looks good.
Okay, great. Yeah, so I'm not actually talking about ship tracks today, although they are really cool. So instead, what I'm going to be doing is talking a little bit about trying to understand changes in clouds over, essentially 3 hours, the difference between the Temporal overpass and the Aqua overpass. And whether we can use that to learn something about how aerosols and droplet number concentration influence cloud development. So we know that cloud adjustments are still a large uncertainty in forcing estimates. There's a scatter plot from a few years ago showing a collection of model estimates and some observational estimates of the cloud fraction adjustment on the x-axis and the liquid water path adjustment forcing on the y-axis. And for liquid water path, even the sign of the effect is uncertain. And Peter's just showed us that if you look at things in a different way, maybe we'd be looking at it wrong altogether. The kind of instantaneous relationships we get if we just kind of look at how liquid water path and droplet number concentration relate to each other typically show us this kind of increase at low droplet number concentration or increase in liquid water path. So as we would expect from wet scavenging. Precipitation suppression rather, and then a decreasing liquid water path at high droplet number concentration, perhaps due to enhanced entrainment. The problem is that we know that there are various retrieval biases that might cause a relationship that looks like this. We have feedbacks from liquid water path to droplet number. So if you increase liquid water path, you can get more rain, which might then reduce your droplet number concentration. And that requires using the time dimension to disentangle this. I'm just going to plug Rebecca's paper as well, which shows that these adjustments can also depend quite strongly on temperature, which might affect how we diagnose forcing under climate change. Now, we know that both models and observations show that these sensitivity estimates change over time, typically getting stronger as you move further away from your initial perturbation. And what we're trying to do here then is to say, well, okay, let's just look at how these clouds evolve. We'll pick two populations, a high droplet number population and a low droplet number population, and see how liquid water path changes over time. So here, D liquid water path is the change in liquid water path from the morning to afternoon. And then delta D LWP, kind of a second change, is the difference between the high droplet number concentration population and the low droplet number concentration population. Now, what we find when we first look at this is that that is positive everywhere. So red means that the high droplet number concentration population, so the kind of high aerosol perhaps population, has a higher liquid water path at the end of this 3-hour period than the lower droplet number concentration one does, or at least it doesn't decrease as much or it increases more. So essentially what we're saying is if you start in a high droplet number concentration case, your liquid water path is enhanced at the end of the 3-hour period. And so this would imply a strong negative forcing from liquid water path adjustments. So quite different from what we see in most other studies. Now, part of the reason for this, unfortunately, is that it's to do with the kind of initial state of the clouds. So this isn't really the real kind of effect. What we have to do is kind of constrain the initial state of the clouds. So what's happening here is a case with high droplet number concentration typically starts with a low liquid water path. And if you have a low initial liquid water path, you're much more likely to increase liquid water path over time. So you get a positive DLWP compared to a clean case, which starts with a higher initial liquid water path and typically then has a negative DLWP. And so that's why you get this positive delta DLWP. If you fix the initial liquid water path, then your high aerosol population typically has a lower liquid water. High droplet number population typically has a lower liquid water path at the end of this 3-hour period. So this is more like what we would expect, and you get kind of a decrease in liquid water path with increasing droplet number concentration. And this seems to happen pretty much whatever your initial liquid water path is. Now we can see a similar kind of effect going on if we look at the kind of opposite. So if we start with high liquid water path versus low liquid water path, how does that affect the droplet number concentration evolution? Can you see the mouse? Maybe, yes, okay, great. Yes. So in clean clouds, with a relatively low droplet number concentration, if you start with a high liquid water path, you typically have a lower droplet number concentration at the end of the time period. And this is perhaps what we might expect from wet scavenging. So high liquid water content, high liquid water path, more likely to be precipitating a stronger decrease in droplet number concentration. But in a polluted atmosphere, we see the opposite. So if you start off with a high liquid water path, your droplet number concentration increases over time and continues to increase as your liquid water path, if your liquid water path remains high. Now, these maps are kind of interesting, but they're a little bit tricky to kind of, I suppose, see the processes in. So what we'll do here is kind of think about them in terms of kind of flow fields. So similar to Franziska Glasmeyer's paper from a few years ago, looking at model results. So this here in the top here, we're just looking at the kind of instantaneous results to start with. And this top plot is showing the probability of a liquid water path given you've observed a certain droplet number concentration. So each of these columns here is the distribution of liquid water path for a given droplet number. And what you see is that it increases, liquid water path increases with droplet number at low droplet number and decreases again as you move to high droplet number. So there's negative sensitivity. If you look at droplet number concentration, it's a little bit different. You typically find that droplet number concentration decreases as you move to high liquid water path, which would be perhaps what we'd expect from wet scavenging. Now, if we look at the liquid water path evolution, so how does liquid water path change over the 3-hour period for any given starting position here? We typically find that if you start with a high liquid water path, you'll typically decrease liquid water path over time, and a low liquid water path, you'll typically increase it. The pattern varies slightly with droplet number concentration, but it's converging to this kind of longer term mean, which is perhaps what we would expect. The droplet number concentration evolution looks a little bit different. And it doesn't seem to quite converge to this instantaneous result that we see. So high droplet number concentrations tend to decrease, low ones tend to increase. And you've got this kind of effect up near the top where things are slightly slanted, which again is suggestive of wet scavenging. But the important point here is that there's a slight negative relationship there. And what this means is that the liquid water path effects on droplet number act as a negative feedback on this relationship. So the instantaneous relationship between droplet number and liquid water path that we use for characterizing the liquid water path adjustments is affected by feedbacks from liquid water path and droplet number. So it's not the causal impact of droplet number on liquid water path. And it obscures that kind of causal relationship, the one we'd need to be able to diagnose. We can learn a little bit more about these droplet number concentration changes by looking at the kind of meteorology fields. I'm going to mostly skip through this, but the point is you can look at kind of where you find precipitation in this droplet number liquid water path space. You typically find it at the top left where effective radius is small, but it varies the kind of exact pattern of it varies quite strongly depending on the resolution and on how you define what precipitation is. So we're actually doing all of this work at 1 by 1 degree. And if you look at 1 by 1 degree, the precipitation doesn't switch from kind of non-precipitating to always precipitating when you move over this 15 micron boundary. That even if you've got a large scale average effective radius greater than 15 microns, that doesn't mean it's precipitating everywhere. And you get a slightly kind of smoother shift. Yeah, let's get through that. Now we've got these kind of flow fields, but one of the kind of tricky bits then is how do we compare this to a large scale droplet number liquid water path sensitivity? And the way we've done this here is similar again to the Glassmeyer paper using model results, is to try and evolve points within this flow field. So kind of our change in liquid water path and droplet number, and see kind of how they move through droplet number, liquid water path space, and where they end up, what the kind of eventual sensitivity is. So this left-hand plot here, the light gray points are the ones we start with. So they're sampled essentially, so that our flow field is maximally sampled, but there's no relationship between droplet number and liquid water path. And then we let them evolve through time. So the dark points here, I think, are at 6 hours evolution maybe. And then the black points here are after 24. And you see this gives us a strong negative relationship. But this negative relationship is actually a little bit weaker if we consider only the initial droplet number change. Right? So because our droplet number has also been evolving, this gives us the negative feedback that steepens the relationship. So if we have if we kind of look at the initial droplet number, we don't include this feedback, and we end up with a much shallower relationship between droplet number and liquid water path. So we can kind of account for these feedbacks. You see the development of this, the strength of this sensitivity with time here. Now this is only approximate because we have to necessarily use a constant flow field here, this kind of DND, liquid water path field. It would be very useful to know kind of how this actually evolves with time, because we don't expect this flow field to be constant with time. And that's something obviously we have to look, thanks Matt, that's obviously something we have to look at with geostationary data. So finally, if we look at the maps of this sensitivity, we see the instantaneous measurement gives us this strong negative sensitivity pretty much everywhere. But if you only look at the initial droplet number, so you remove this effect of wet scavenging, the sensitivity is a lot weaker. And in this case here, it typically peaks at about -0.2. So that's still offsetting around half of the Toomey effect, but only in the kind of center of the stratocumulus decks. So as a summary, some of this is obvious, I suppose. Liquid water path adjustment to aerosol is complex. The temporal development gives us a way of accounting for some of these feedbacks, but the initial state you use for that temporal development is really critical in terms of what answer you get. These kind of flow fields give us a bit more detail on how droplet number and liquid water path might evolve, and allows us to look a little bit at the different processes, particularly things like wet scavenging. And if we evolve these points in the flow field, it gives us a way to compare these kind of more complex diagnostics to a simple droplet number liquid water path relationship. Suggests that it might be slightly shallower, but there's a lot of uncertainty there, because, as I say, we necessarily have to use a constant flow field here, which is something that we know is probably not constant. Cool. I think that's everything. Oh yes, okay, there's a paper. I say submitted because I finally finished it this morning, so. Cool.
Great, thank you. Are there any questions for Ed? We have time for one quick question.
Okay, talking a bit too quickly.
I have loads of questions, but I'll ask one quick one. If you were to think about, this is a nice 3-hour time period between Terra and Aqua. If you were to think about longer or shorter time periods, do you think that would influence the results? Like, for example, maybe a full day between Terra and Terra on days, or even shorter with geostationary down to like an hour time scale?
Yeah, well, I think the kind of longer scale trajectories that you looked at are kind of the, I mean, that's getting closer to the timescales that you'd actually want. So I think that if you can get kind of longer timescales, that would be interesting as well. I think one of the key things here is that we expect these processes to vary at different times of day. Now, unfortunately, cloud microphysics retrievals at night are a bit difficult, but it would be really useful if we had them.
Indeed. Okay, great. And we have one speaker to end the session. Last speaker is Manoush, talking about impact of Halloran volcano aerosols on clouds in cloud system resolving simulations.
Yes. Hello, everyone. Volcanic eruptions can influence the climate on different perspectives. For example, they can influence on the radiation budget of the Earth, so the dynamic of the atmosphere, and also the hydroclimate. But here in this talk, we focus on the tropospheric aerosol emitted from the volcanic eruptions, particularly sulfate aerosol as a natural laboratory, which can impact the clouds. These eruptions can help to understand how additional CCN or cloud condensation nuclei influence liquid water clouds. So here, as a case study, we chose Holoran volcano, which is in Iceland, erupted in 2014. Our method relies on using the ICAN model in the number weather prediction mode and also using the satellite observations. So we performed a regional domain simulation over North Atlantic, as you can see here in this picture, with the horizontal resolution of approximately 2.5 kilometers. We used the double moment macrophysics scheme, and as an initial and the boundary condition, we used the ACMW reanalysis. And the duration of the simulation is the first week of eruption, from 1 to 7 September 2014. An additional feature that we used in the simulation was to use the satellite simulator, COSP satellite simulator, to improve the comparison between the model simulations and the satellite retrievals. So the the model that I use here doesn't include an interactive aerosol model. So the method that I used to implement a volcanic plume in my simulation was to use a lookup table that contains a number of activated CCN as a function of vertical velocity as an input for simulations. In order to create this lookup table for simulations, I used the CAMS reanalysis to get to the aerosol compositions. And then I applied the Abdul-Razak parametrization, which is nothing but correlatory, to get to the activated CCN concentration as a function of maximum supersaturation. But still, I needed to know how the plume evolves during the simulation. So in order to get to this state, to this profile, I use the OMPS satellite retrievals, which is monitor sulfur gas. And this is the evolution of the plume here in this period. So based on the enhancement of the sulfur gas in the lower troposphere, I scaled the number of the sulfate aerosol in CAMS reanalysis. Then I performed this Abdul-Razak parameterization, and I got to the profile of the perturbed activated CCN. This figure shows what I was talking about. This is for just one day, for example, 2nd of September. Panel A and C shows the profile of the CCN for two different vertical velocities. The background concentration of the sulfate was used here. And in the panel B and D, I brought the scaled profile of the CCN, which contains the volcanic plume. As you can see, as the vertical velocity corresponds to the supersaturation, the higher vertical velocity, at higher vertical velocity, the more particles get activated, and we have the higher concentration of the CCN. So the idea here is to compare how the microphysical variable in simulations and also in MODIS behaves differently for region inside of the plume and outside of the plume. For example, here you can see a PDF for the cloud droplet number concentration for outside of the plume and inside of the plume. So if you consider the profile for outside of the plume, we can see that the curves are pretty close to each other. This is for the volcano, no volcano simulations, and also compared to the MODIS, which shows that the ND profile in MODIS is considerably close to the simulation. This fact can also be seen when we compare the mean values of the ND for MODIS, no volcano simulation, and also volcano simulation, which are pretty close to each other. But if we consider the profile for inside of the plume, we can see that in the volcano simulation, the ND probability over larger amounts are clearly enhanced compared to the volcano simulation. And this is in the better agreement with MODIS. So in the MODIS data, we also obtain these higher probability for the larger cloud droplet number concentrations. We did also the same analysis for liquid water pass. Again, for outside of the plume, the profile are pretty close to each other because we don't have an additional CCN in outside of the plume, but for inside of the plume, we can see that in the volcano simulation compared to no volcano simulation, there is a decrease in the probability of the cloud with lower liquid water pass and increase in the probability of the higher liquid water pass between these two simulations. And this enhancement for the larger liquid water pass in MODIS is something between these two simulations. If we compare the MODIS profile for inside and outside of the plume, we can see this decrease in the lower liquid water pass and increase in the higher liquid water pass. But the mean enhancement between inside and outside of the plume for MODIS is considerably lower than what the simulation shows. We also looked at the rainwater pass profile just for simulations. And if we compare it inside of the plume, we can see that in the volcano simulation, there is a decrease in the less rain and then increase in the probability of the heavier rain. So here we conclude that with the clouds with the higher cloud droplet number concentration and the smaller size, they need to grow deeper to reach the size that they can start precipitate. So the rain is suppressed, and therefore the clouds must grow deeper, and this shift the liquid water pass profile to the higher values. And when these deeper clouds start to precipitate, they precipitate more heavy. This also can be seen that in the volcano simulation, the mean of the rain decreased compared to the no volcano simulation. We also analyze the cloud fraction just in terms of the mean values. We can see that in the volcano simulation, we have about 8% increase in the cloud fraction. For MODIS, we have higher cloud fraction inside of the plume compared to outside of the plume, but it was not very clear that this enhancement is attributed to the additional CCN or is just the different meteorology condition.
2 minutes.
So here I come to the summary. I use the ICANN and WP to simulation Holoran volcano. We developed a method to interpolate the number of activated CCN, and we determine the plume using the OMPS satellite retrievals. Then we observe an enhancement in the cloud droplet number concentration in simulations and MODIS, and we get the shift in the liquid water path distribution to the higher values. So thank you everyone for your attention.
Great, thank you. Are there any questions?
There's one in the chat, Matt, from Ed. You want to just ask it, Ed?
Yeah, sure. Thanks, man. It's really interesting.
Yep.
The plot you showed of the precipitation or the rainwater path, I think like one slide back.
Yes.
And you had an increase in kind of heavy rain inside the plume. So you also get a slight increase in total rain, or?
In total rain, it's this is logarithmic scale, so it's not a very considerably like large in total, I would say. These differences between outside of the plume, if you mean, if I understand you correctly.
Well, I was thinking inside the plume, the difference between your volcano and no volcano case. What's the difference total?
The total, I mean, I didn't calculate the total rain for the whole time, but for inside of the plume here in the table, you can see that the rain decreased, for example, for volcano, the enhancement of the rain inside of the plume is 38%, and for no volcano is 53%. Yeah, so about 15% decrease in the rain.
Okay.
Yes.
Cool. Thank you.
Great. Thank you. And Ralph Kahn has a comment in the chat if you'd like to read that. And
Yes, sure.
in that case, I believe that brings us to the end of the talks, and just would like to thank all of the speakers for your contributions. This was fantastic. And I think now we move to a break. Andrew, do you have any?
Yeah, thanks, Matt, for running that great session, and thanks to all the speakers. I think why don't we take a break for 15 minutes till the top of the hour? We'll do that, and then we'll come back and do the posters at that point. So we'll take a break until the top of the hour, so 15 minutes.
Great, thanks.
And Matt, I can, if you want, I can do the posters again if you want.
Oh, yeah, okay, that would be great. Cool.
Okay, great. I see Gion's already ready to go. Let me see if I can get somebody else to display the slides, because it just makes it harder for me to do several things at once. But I guess I can.
Andrew, I think Yitran can help you. Let me see whether Yitran is
Okay,
still.
if not, I can do. You know what? I can do it. I can just do it in the window. Let me do it.
Okay, good. Thank you.
Maybe
I can
I
do it.
can share. Okay.
Either way, let me just get them sized up. Whoops. Okay. So let me see how this is going to work. Hopefully it will work okay. Whoop. There we go. Let me just make sure they'll all reasonably, yeah, they're basically all coming in at the same size. Okay, so let me go ahead and share that. Okay, is that visible?
Yes. Can you hear me?
Yep. Does that look okay?
Yep.
Okay.
Okay. Hello.
So let's see. Gian, why don't you go ahead? We'll do poster presentation.
Hello, everyone. This is Jaeyoon. And in this work, we simulate and investigated 2-day LES simulations of subtropical marine low clouds under 5 different meteorological conditions. The main purpose of this study is to understand microphysical, macrophysical, and radiative responses of marine low clouds to aerosol injection. As shown in the schematic in the middle of the screen, there are complex responses and they are quite sensitive to background meteorological conditions. In the breakout room, I will illustrate the complex responses in detail and how they affect the cloud properties. I'm looking forward to seeing you soon. Thank you.
Great, thanks. Next is PornPy.
Hi everyone, so this is Ping Ping or PornPy here. Today I'm going to explore the impacts of radiation on shallow cumulus transition and cloud organization. Here the radiation is modulated by the diurnal cycle and the mineral dust above the cloud. The case study shown in the top left is based on a sugar to flower shallow cumulus transition observed during the atomic and eureka field campaign. In the first part shown in the bottom left, it's clear that the diurnal cycle has a strong impact on the clouds, particularly on the cloud amount and the organization strength. In the second part shown in the bottom right, we explore the radiative impacts of the mineral dust on the clouds. During the day, the free tropospheric mineral dust blocks the shortwave radiation, cools the clouds below, helping to strengthen the mesoscale circulation that drives the transition. Overall, the response to the diurnal cycle is much stronger, but the radiative impacts of the mineral dust should not be neglected. And I look forward to talk to you more in the breakout room. Thank you.
Great, thanks. Yang.
Hello, this is Yang speaking. I'm Yang Zhao from Nanjing University. Based on long-term satellite observations, we found the hemispheric contrast of ND was nearly halved during the last 2 cases, mainly due to the emission reductions. As a result of emission reduction, we found clear Toomey effect, but for the cloud lifetime effect or cloud cover effect, we need more effort. The third point is although the fine LOD or AI replicated the contrast trend, but it poorly correlates with ND. More details will be shared in the discussion room. I'm hoping to see you then. Thank you.
Great, thank you. Next is Hao Wang.
Hello everyone, I'm Hao from Nanjing University, and my topic is the response of LWP in Chem6. The sensitivity of liquid water paths can be negative by joining from the increased entrainment of the overlaying air, and this process is not considered in most GCMs. In my previous research, the calculation of subgrid cloud water variance is improved with this formula, and the sensitivity of liquid paths to aerosol is decreased. So we further want to check if there is negative response of LWP, which was found in the LES and the single colon Chem6 in the previous research. We select the typical straight cumulus region over the southeastern Pacific and select the marine single layer cloud with small relative humidity above the boundary layer heat. We can see with the increase in cloud top CDNC, the LWP decreases and the entrainment rate and the third moment vertical velocity from the cloud increases too. This means the increased entrainment and the interaction between the cloud top and the dry air in the upper layer can be caught when the RH is small. I can share more detailed information in the breakout groups. Thank you.
Thank you. Next, Persona Fani.
Hi, everyone. This is a work by the MCB group at the University of Washington. We conducted Lagrangian LES experiments by using SAM coupled to the Berner aerosol model. As shown on the bottom left, two CSAT Lagrangian trajectories are selected, LO6 and L10. Multiple runs with different free troposphere and initial boundary layer aerosols are conducted. A few selected results on the right. Here, each point shows the one LES run averaged over the runtime. For LO6, which is a precipitating case, the runs with enhanced aerosols show enhanced cloud radiative effect, liquid water pass, and low cloud cover. However, for L10 case with weak precipitation, macrophysical variables are not too sensitive to aerosol change. Thank you.
Thank you. Next is Halang Ji.
Hi, this is Hailin. Today I'm going to talk about some of difficulties in quantifying the TUM effect from satellite observations and to discuss how much those issues could over or underestimate the TUM effect. The equation here shows how we generally calculate the relative forcing due to TUM effect from the observational perspective, in which the sensitivity of ND to aerosol is the most challenging part because it's difficult to disentangle any aerosol effect from other possible confounders. In this study, by using the multi-sensor satellite observations and also the reanalysis data, we demonstrate the dependence of the TUM effect or the ND sensitivity on several major confounders, including the updraft, precipitation, retrieval biases, and also the vertical collocation. That's all. Thanks.
Thank you. Next is Allison.
Hi, I'm proposing a benchmark data set of clouds and aerosol in the Southeast Pacific. And this is so that we can look at how the different methodologies that we've all adapted actually might impact our results by using the same data set to repeat the same experiment. So this would be at the swath level and is graded at 25 by 25 kilometers and includes reanalysis aerosol from MERA, CAMS, and then environmental information from AERA5 and MERA. And this can be compared against both the Terra and Aqua satellite overpasses. And just repeating a couple of different ACI studies, we can already see that there are differences based on using AERA5 / the CAMS reanalysis versus MERA2. And that also sometimes the methodologies themselves might introduce some bias if we alter the binning or try to kind of smooth the parameters of the model that we're using to fit a little bit. So, yeah.
Great, thank you. Next is Michael.
Yeah, so this work on the slide here is about an LES intercomparison study looking at the stratocumulus to cumulus transition and really focusing on this question of under what aerosol situations do you get kind of this classical transition not mediated by precipitation versus under what conditions do you get a precipitation mediated transition? And if you're interested in this, please reach out and email me, because for the poster session today, we're actually going to talk about the MCB roadmap, because it looked like there was quite a bit of discussion there and maybe things that people want to talk about more. So come to my poster session if you want to talk about the MCB roadmap.
Thank you, Michael. So to reiterate that, we're not going to talk, he doesn't want to talk about his poster. He actually wants to talk with anybody who's interested in marine cloud brightening and some of the work that Graham described earlier. So his Michael Diamond's breakout room can be used for that. Thank you. Next, Manisha, Mara.
Hi, this is Rebecca Sheasley. Can you hear me?
Yep.
So Manisha had a baby 2 days ago, so I am giving her a little presentation now. So congratulations to her. We did a brief campaign near the Tracer AMF site in Houston last September, comparing the presence of coarse black carbon versus fine black carbon, which is of interest, I think, in terms of understanding potential aerosol effects in Houston on convective activities. But the interesting thing, of course, is in Houston, we actually have a significant amount of coarse black carbon, which might be unanticipated in terms of the model studies that are being done. So if you're interested in learning more about coarse black carbon in Houston near the Tracer site, please stop by. Thanks.
Thank you. And last is Shiro Joshi.
Hi. Black carbon, I'm Shiro Joshi from Michigan Tech, and black carbon containing particles change in morphology and mixing state in the atmosphere due to aging and cloud processing. So the main objective of the light absorbing aerosol cloud interaction project is that we study the effect of interaction of black carbon containing particles with clouds in the Michigan Tech's cloud chamber. And so far in the project, we have injected black carbon into the cloud chamber in dry conditions as baseline experiments. And currently we are carrying out some preliminary experiments with humid conditions using a pump counterflow virtual impactor to separate residual and interstitial particles. And if you want to hear more about the project or have any comments, please join me in my breakout room. Thank you.
Great. Thank you very much to everybody. I think we got everybody. I will stop sharing and I'm going to open the breakout room. So you should see those available. So as before, we're going to, thanks to all the speakers for keeping on time. We'll do this for a little over a half hour. We'll probably come back at something like 1:45. We'll have a 15-minute wrap up at that point for discussion. But once again, based on the posters, pick 2 rooms, first 15 minutes or so, one room, next 15 minutes or so, the other room. So there'll be somebody here in the waiting room if you have trouble, but you can leave by just hitting the leave breakout room button. You can come back to the main room, or you can just join by hitting breakout rooms. You can move directly between the different breakout rooms. So please feel free to move to your rooms. We'll have some presentations and discussion in those rooms. And after about 15 minutes or so, we will actually ask people to switch and you can do it again. So thank you very much, and we'll see how this goes. Let's see if anybody has trouble, just you can say something, you can speak up in the main room. We'll stay here for a few minutes until we move over, and then, or you can put something in the chat.
Sorry, I'm trying to do this on my phone. I don't know where do I?
I'm not sure
does anybody
where.
know if that's
I'm not sure where it is on where breakouts are on a phone. Usually there's some extra dots.
okay?
But that's okay if you can't make it.
Yeah, I think this format worked pretty well yesterday, Andrew. The reminder was nice, I guess, halfway through to sort of switch.
Okay, yeah, I think I'll send a reminder at like 9:27 to switch in 2 minutes at 9:29 or 9:30.
Rebecca,
Great.
if you know what session you want, what poster you want to go
Oh yeah,
to,
I can put,
and move
yeah,
you
which
over.
I'll just put you in, I can put you in that room. That's,
If you
I
can just
forgot
put
about
me
that.
in Manisha's room, and then I'll
Yeah.
just, that way I'll just be there if anybody does show up. But
Right.
yeah.
There you go. In case you want to. Otherwise, you don't have to if you're there. So that should work.
Thank you.
Did you go already, or let's see what happened? I thought I did.
No, she did.
She did. Okay, great. That works. All right, I'm going to jump off to one of them.
That was the first time in all my meetings that I had someone join from their car while driving.
So hopefully people are moving around.
Recorded. Meeting is being recorded.
Okay. Welcome back. So hopefully that went well. I saw there was a bunch of discussion in a number of the different rooms. So now we have time to kind of summarize things for today's talks, and there's quite a bit going on. So I think I had a couple of comments that maybe I'll start with, and then I guess Matt can jump in, and then we can see what other people's comments are. It's some really interesting, I mean, the summary sort of, we had a couple of discussion. We had basically discussion of ship pollution and volcano tracks in the talks. We talked a little bit about marine cloud brightening as a research program, and looked like Michael's discussion room is pretty active on that. A couple of talks on volcanoes, one on pollution tracks, a couple of really interesting results on machine learning for finding ship tracks, and also using location data to find invisible tracks, and then looking at the time evolution, which I think is a good summary of kind of where a lot of the really interesting active work are. And there was a lot of interesting things in the posters also relevant to that, looking at some of these things, changes in liquid water path and models, and looking at evolution over time of cloud properties in response to changes in emissions in some of the posters, at least the ones that I saw. Discussion wise, I thought, where's my summary? So it seemed pretty obvious that the initial state of drop number and liquid water path is governing the magnitude and the sign of response. We saw that in a couple of different things, and there's some really interesting relationships that are coming out of these different observational methods. I guess it's useful to sample models in the same way, and we can start to do that across scales because there's some interesting perturbation models that people are using for volcanoes. This shows some large-scale responses that actually match both the observations and then some that have the biases. So there's some interesting scale separation. I think machine learning is really making a difference for some of this pattern recognition and finding ship tracks, and I think the ship report stuff is very interesting. And there's some estimates of radiative forcing with these different methods. So again, that's hard to scale up and match the models because of the difference in methods, but maybe there's ways to actually do that with cross comparisons or doing those sort of scaling activities with the radiative forcing, and people are doing it offline, also with model analysis. And there was lots of interest in marine cloud brightening. And then I think, again, thinking about what are the next steps for ACPC and where can we work together. It sounded like there may be some opportunity. Duncan sounded like the ship track observations, the data sets may be available in process form, which would be kind of exciting once that paper is published. That's kind of what I saw. Matt, did you have any comments on that or other thoughts?
No, I think that's a really great summary. And I think there's, a couple extra things that I noticed is that there seems to be widespread consensus on, the general Toomey effect, that these polluted clouds have reduced droplet sizes and there are more of them. But there were two talks, I guess, looking at volcanoes where there was a difference in liquid water path direction and sign. So, and then cloud fraction responses are still quite variable amongst these studies, I think, despite a wide range of new methodologies and tools. So that's still obviously a problem that needs to be dug into further. And then we're sort of at a nexus, I think, between marine cloud brightening studies, ACI, and natural laboratories. So there's quite a lot of synergy there to discuss as well. And so those are my thoughts.
I would like to add that cloud cover can potentially have very large effect, but it is the least studied. And one contribution for that is just its definition is poor, and you could see quite a large uncertainty in MODIS cloud fraction, and when you compare it to higher resolution satellites, the cloud fraction there is larger. So this needs some attention from our community.
Which is interesting because you'd think cloud fraction, especially over the ocean, is the easiest thing to observe.
Not at all.
A lot easier than, say, drop number or liquid water path, for example. But as you're right, and we've had the same problem with models, is defining a cloud is very difficult. And so that when you're doing analysis, you have to be very careful that you have a consistent definition of a cloud. So part of it is just self-consistency, but it also means, like we've seen now with liquid water path and drop number, different clouds, so different regimes of cloud fraction are going to have different responses. So if you're looking in different instruments, you may see a different response, right? Because you're looking at a slightly different part of the PDF.
I think
other comments.
Yeah,
ahead,
I would like to make some comments. So I think a couple of things. One thing is time scale. So I mean, today we have a lot of aspects, probably not a lot, but several talks. They are addressing or is relevant for the understanding the time scale. I think one is the like use geostationary satellite. I think that's really a good tool, and I see Wallace talk started to looking at that. I think it would be great if we can see more of that, see how the observations show that. I think that's a poster by who? Let me see. Yeah, Ye Yuan. I'm not whether I pronounce it correct. I think he also shows some of that. So how the response in the second day become stronger in terms of the liquid path response. I think so. I think here probably opportunity say how combine models observations together to see how exactly some of the previous finding will be revealed in more extent. I think that's one thing I take from this. And second, I also second what Danny just said is cloud fraction. It seems the cloud fraction response was. I think it has not been well accepted in the community, but I think we're glad to see there's some talks today are related to that. It seems Tina's talk shows a response from cloud fraction. I think we also see other talks, they also show a response from cloud fraction. So it seems the cloud fraction, now we have some ways to understand that. So I think as Danny mentioned, we probably want to focus more on that in the future study as well. And the third point is the marine cloud brightening. I think Matt and Andrew and with a lot of others made a really excellent review paper just published last year. I think that's really excellent work. But then for the marine brightening, I think that's I probably want to see whether we can do more for this group. I mean, like Graham outlined 6 topics, but first 3 probably align well with the focus we have, whether we can do something more. I think that's another thing is probably we also want to think about whether we can start some new initiatives here related to those issues as a group. I think that's why we have the ACPC meeting. Okay, thank you. I just because it's comments.
Thanks, Mimai. Other comments?
So it's great to see all this work on tracks and natural experiments. So I agree, Andrew, that the end goal would be models, observations, intercomparison, or evaluation of model quality. But there are clear difference in the methods we use studying these tracks and natural experiments, and this gives slightly different results, sometimes very strong disagreements. So I would suggest that first step would be intercomparison of the observational data sets and methods, if this can be achieved, because small difference matter. It seems that it's fairly similar, the methods, but small difference do matter. And if we see some aspects what are very robust, this would be a good result in itself.
Right, although, yeah, I might push back on that, which is related to what we were just talking about with cloud fraction, which is you can actually take a model and you can run your method on the model output to the extent feasible. And if different methods produce different results on what we know is exactly the same geophysical state in the model, then we know there's a difference in methods. So the models can also be used as a transfer function to evaluate the methods. So for example, it's like comparing to two different satellites that see different parts of the cloud fraction. You can generate two different cloud fractions in a model which represent what the satellites would see. And if you run that through a methodology, you may get a different answer, but we know the model has one response in some way. And so it's sort of like, it's basically like being able to, it's like the blind people looking at the elephant, right? You want to be able to look at all the different parts of the elephant, and the model is the uncertain elephant, but it is a consistent elephant. We just need to see all pieces of it. So I actually think even if the methods don't fully agree, we can actually try to bring the models to each method and intercompare also in that way. That may actually help us with the transfer function. May not help us so much with the ship tracks because most of the models are not going to get that level of detail, but it may help us with some of the other responses.
Hi, Andrew and all. So yeah, this is an interesting discussion point. When we do observational sort of modeling intercomparisons, there are many ways to do it, right? For example, maybe one way to do it is just to come up with really one-dimensional relationships. Just give me an answer, what kind of cloud response we should expect to get in both models and observations. So more simplistic. And then there are ways to really get into the process level. Do we want to, which way is better way to go? I think there's benefit and pitfalls in both directions.
I think you kind of want to do both. It depends on the interest among different groups. I think subsets of groups can either do larger scale or smaller scale. I mean, there's some really interesting now, you know, the small scale models we saw of the volcanoes, I think are pretty interesting, potentially looking at processes. So I think you do both, and they maybe do, it's not like we're going to do, maybe it's not one intercomparison, but it's, you know, groups of people that are interested in working together at different scales. And we can, you know, the global models can produce some process level information to the extent possible. I mean, not at the mic, you know, to some, you know, we can produce size distributions and process rates to compare in detail. We can also produce averages. So, and we can produce time series. If people want to look at time scales, we can come up with diagnostics for that. Other thoughts or comments?
Just thinking about the cloud fraction definition. I guess I had a quick look, maybe doing something similar to what you said, Andrew, was using the model as a test bed, I guess. So I looked at defining the cloud fraction using an optical depth threshold versus a liquid water path. So I guess when you increase the dropout number, the optical depth increases. So you kind of get an artificial increase in cloud fraction almost because of the increased ND, Twomey effect. Whereas the actual clouds themselves don't change.
The way to do that is by forward radiative transfer model that will replicate the satellite channels and then see what you retrieve based on what you know is model truth.
And we actually have that for the A-Train sensors in the COSP simulator, for example. There are about 4 or 5 different cloud fractions that come out of that simulator that do that radiative transfer modeling. So that might actually be interesting because we could do that in perturbation experiments to see if you could lock clouds in some way and change drop numbers, run it through those simulators and see if the cloud fractions actually did change. So those experiments are kind of possible.
We actually did that in LES at some point using either optical depth or liquid water path thresholds. And you see how different your responses look sometimes to an aerosol perturbation.
Okay. this paper. Is that great?
Yeah, Andy, Andre, I have another comment to the cloud brightening community. I think you should think very hard about the attribution question, given the fact that it has taken decades, basically, to come to a conclusive attribution of climate change as a result of greenhouse gas forcing, which is a much larger forcing than anything you could dream to achieve with marine cloud brightening. It would seem plausible to me that it would take actually decades of a forcing that's equivalent to at least the entire sulfate forcing to be detectable over natural variability. So in other words, you'd have to probably deploy anything like the entire fleet of potentially cloud brightening ships over 2 decades before you could actually prove that you've done something. So I think that's something that one needs to think very carefully about.
So Andy, one of the checkpoints was detection, and there are at least a couple studies that essentially say what you just said, which is that it could take about a decade to detect changes in albedo. And of course, it depends on, with what confidence and at what level of albedo change. But certainly that has been thought about, and I can send you some links to a couple of papers. One of them is Michael's shipping lane paper. The other is an earlier Nature Climate Change, Diane Seidel et al.
Yeah, I mean, I'm aware of that, and my point is that my sense is that that is a checkpoint that is likely never to be achieved, or unlikely to ever be achieved, just because of the magnitude of the effort required to produce an effect that's detectable on a strict attribution sort of level. And that ultimately means not detecting albedo change. That means actually detecting temperature change, because that's where, or climate change, because that's where the rubber hits the road. So doing something for 20 years without actually being able to distinguish it from natural variability seems scientifically questionable, but maybe politically justified, because doing something is politically always more justifiable than doing nothing in a case like this.
So let's pull back from politics a little bit, since we're at the top of the hour. And
well, yeah, I mean, the geoengineering is 99% economic political question and 1% scientific, I think. So we can't just say, oh, we're scientists, we're just totally agnostic of anything political or economic.
Well, thank you for raising that, Andy. I'm going to give Tianli the last word, I think, for today, and then we'll wrap up.
Oh, I just want to follow up with the cloud fraction comment. So because since it's kind of like a philosophical question, and technically, do we want to come up with some sort of criteria, since like you mentioned, the self-consistency is a good sort of metric we could follow, because people might fight over the definition of cloud fraction changes. Do we want to say something about that technically, not philosophically? Philosophically, it's harder, I think.
Yeah, I think it's probably just, if we're going to look at comparisons or start working in the space of looking at cloud fraction effects, we need to be very careful at making explicit how clouds are defined, so that we can separate out the methods, because if we get conflicting results, you don't want to compare them if we're not comparing apples to apples. But I think that's a great point. So my thought would be, the criteria would be, the self-consistency that we've been discussing, and trying to encourage comparisons that are cognizant of the differences, rather than trying to say cloud fraction increases, no, it decreases, when those are different.
Yeah, I agree. Oh.
Go ahead, Matt.
Yeah, I agree with that. And just to follow up as well, in terms of regimes, different cloud regimes or thermodynamic regimes that can be different and have an influence on the cloud fraction response is also very important. And I think Alison Douglas, her poster sort of describes all these different methodologies to apply to different data sets. And so we could think about, how to define regimes as well as how do we define
Right.
definitions for cloud fraction.
And we've seen a lot of different regime-based analysis now, which I think is great. A lot of what we saw today. So, okay, well, on that note, I think we'll close out the session for today and say thank you, everybody. We had 96 people at its peak today, so that's great. And we'll see everybody tomorrow. Thanks.
Bye.
Thanks.
Bye.
Bye.